Hello everyone, I'm Liu Huimin from Tencent Security Xuanwu Lab. Now we will present you our talk, a mirage of safety, bug finding and exploit techniques of top Android vendors' privacy protection apps. First, please allow me to introduce ourselves. We are from Tencent Company, and my department, Tencent Security Xuanwu Lab, is one Tencent security research lab based in Beijing. We focus on the various applied and real-world security research and report hundreds of vulnerabilities to world-famous vendors every year. My colleague Zhang Xiangqian focuses on mobile security and found multiple Android kernel and system security vulnerabilities. And I focus on mobile and IoT security. And this is my third time here at Black Hat Asia. This is the contents of our talk. First, I will present you the introduction of the privacy protection apps and the threat models about them. Then my colleague will detail all the vulnerabilities and mitigations, and finally the conclusion. Let's begin. We all want to keep our privacy and our secrets hidden and safe. So nearly all top vendors develop and provide us some privacy protection apps, such as Secure Folder, Private Space, Safe, AppLock, Lock, etc. They can be categorized into three types. Type 1. Protecting the file access, such as Safe, FileSafe. Type 2. Protecting app usage, such as AppLock. And Type 3. Private isolated space, such as Secure Folder. This slide shows some examples of the three types of privacy protection apps. The left picture shows FileSafe. The user can store their file in it and protect them by setting a password, and the files will be encrypted. The middle picture shows AppLock, which can protect users' apps from unauthorized usage. The right picture shows Private Space and the Secure Folder app, which can isolate multiple apps at the same time. We investigated the privacy protection apps released by top 5 Android vendors, and the result is shown here. All of them released at least one type of privacy protection apps, and 2 of them released all the 3 types of privacy protection apps. But the question is our privacy really safe? So we begin our research. Let's talk about the threat model. Privacy protection apps protect files or apps or space with an independent password or other authentication method. So we expect them to keep files or apps or space safe even after the attacker breaks into the normal world or log in the normal Android OS. What privacy protection apps designed to protect? For FileSafe, attackers cannot retrieve and decrypt file without valid authentication. For AppLock, attackers cannot use the app without valid authentication. For Private Space, attackers cannot access or modify or insert anything in it without valid authentication. Attack scenario is as follows. A1. Attack from malicious apps. A2. Attackers can attack from malicious apps which can gain system privilege. A3. Attackers have physically compromised the phone. Our expectation is attackers cannot get anything when A1 or A2 or A3. If they cannot make our privacy safer, why the users bother to use them? So, this slide shows our expectation about which attack scenario can compromise them, or no. But the fact is, all of them can be compromised. My colleague Zhang Xiangqian will detail them.
Thanks, I'm Zhang Xiangqian. Next, I will show the vulnerabilities, examples, and mitigations. There are many vulnerabilities, and we choose 4 of them to present to you the details. There are typical and good examples. Vulnerability 1. Steal data from the safe from malicious apps. Generally, you can move the secret files to safe and set the password, and the app will encrypt the secret files. Then attacker can't retrieve the file without the password. But we found that the encryption here is not safe at all. In this case, the encrypted files are stored in the SD card. The encryption algorithm is AES CTS no padding. Sounds good, but the key generation is not safe. The key is generated by the device ID. This picture is get device ID function. If the app could get the MEI, the key will rely on package name and MEI. If the app can't get MEI, it will use the MAC to generate the key. If the app can get neither of MEI or MAC, the app will use 10 zeros to generate the key. So it only relies on the package name MEI MAC, which any malicious app could get. That seems a very simple vulnerability, but the case is not alone. This is another example. The encryption algorithm is AES ECB no padding. The key generation is such a fixed string. We also found that another safe is encrypted by XOR with a single byte. We let a malicious app as a demo. First, we get the encrypted file from the SD card, and then decrypt it. Let's see the file safe. There is nothing. First, we take some pictures. Then move it to the file safe. The malicious app can get all the data from the file safe. Next, vulnerability type 2. Retrieve the safe's plaintext password from the trust zone. In our research, we found that some vendors use trust zone to protect the files. We are happy to see this because the trust zone is capable to protect our privacy very safe. If the vendors store the key and the data in trust zone rightly, the hardware architecture will guarantee their safety. In the introduction of the Safe app, it says that the password is not stored and can't be restored. Our expectation is this. Step 1. Input a password. Step 2. The failsafe app sends the password to TE interface to check. Step 3. The TE interface sends the password to check to trust zone. Step 4. If the trust zone app is responsible to check that the password is valid and return the result. Step 5. If check OK, the TE interface will send the message to the failsafe app. Step 6. The failsafe app will use the input password to decrypt the file and display it to user. Step 7. The user gets the decrypted file. So the plaintext password never leaves the trust word. However, the factor is this. In step 3, the TE interface gets the password from trust zone. Step 4. The trust zone app will return the plaintext password to normal world, and then compare it to the password which user input. If checked OK, the user gets the decrypted file. So the plaintext password leaves the trust word. It will not save anymore. Then the left picture shows the function to extract the password from trust zone. The function's input is box folder name, which is the failsafe's folder name, and the return value is the plaintext password. The right picture shows our explorer output. We can see that we can get all the failsafe's plaintext password from the phone. Then let's move on to vulnerability 3. Bypass the privacy password. We found that almost all privacy apps can be unlocked by fingerprint, as shown in this slide. But the privacy apps failed to check the fingerprint is new added or not. So the attacker can add a new fingerprint to bypass the authentication. And also we can reset the password with the SMS verification code on some vendor's phone. This is a demo. First, let's see the private safe and the app lock. We can enter. Next, we just add a new fingerprint. Now we can use the new fingerprint to enter the private safe and the app lock. Finally, let's talk about the last type, private space apps. In the introduction, the vendor said the users can create a secure space on your device to encrypt and store your private data and apps. Apps and data in secure folder are sandboxed separately on the device and gain an additional layer of security and privacy that further protecting them from malicious attacks. The secure folder seemed very safe, so we were curious about its implementation. We reverse engineered the app and we found it called Android User Manager Multi-User API to create another user. This is the output of artificial command PM-list users. It confirmed our guess, and when we activate the secure folder, another user named the secure folder will be added in the system. Also, Android multi-user. Android supports multiple users on a single Android device by separating user accounts and application data. For instance, parents may allow their children to use the family tablet. A family can share an automobile, or a critical response team might share a mobile device for on-call duty. There are three types of users. The primary user is the first user added to a device, and is the administrator and has special privileges and settings only it can set, and it can impact other users. The secondary users and the guest user can't impact other users. The user data are stored separately on the device. Here is the data path, and there are some commands for us to manage other users and the primary users. For example, PM, AM, ADB install, and so on. And we can use content provider to read or write other user data. Our expectation is PM, AM, and content multi-user command will be patched. This command will be on the blacklist, so the primary user can't install or control apps or access data in secure folder. However, the fact is they are not patched. The primary user can install and control user install apps and access any data in it. So we can break the private space by this command easily. For example, we can install malicious apps by using ADB install command, start any app by mstart, and we can grant all permissions for any app using ADB shell PM grant, and store data from secure folder by content write and read command. This is a demo. First, let's see the secure folder. There is an official WhatsApp. It doesn't have any permissions. After we exit the secure folder, we need to enter a password to enter again. Now the attacker ran an exploiter script. Then the official app has been replaced with the malicious app in the secure folder, and it has all permissions. Then we will show how to steal files from a secure folder. First, the user take a photo in the secure folder. Then the attacker can steal the pictures from the secure folder. This is a common vulnerability. All the private space based on multi-user can be exploited. Finally, the advice and mitigation for developers use the trust zone properly. SD card is not safe at all. Don't use it when you are very careful about your privacy. Don't use MEI Mac as key or to generate key. Use Android ID will be better. Android ID varies for different apps. prevent local attacks. For users, don't rely on privacy protection apps, and keep good security habits is more useful. Nearly all of vendors develop and provide us some privacy protection apps, such as Secure Folder, Private Space, Safe, App Lock, and so on. They claim that saving private files in those apps will be safe. However, we conducted comprehensive research about them and found that it's not true for most of them. Many design and development flaws allow attacks to bypass the protection and access the private files inside, which will affect billions of users. We presented 4 types of vulnerabilities and advices for developers and users. By sharing our research, we want to improve the security of the privacy protection apps and better protect users' privacy. Our vulnerabilities are reported to vendors in April 2020, and most of them are fixed. Thank you for listening.